Good afternoon. Today I would like to present some preliminary findings of our study of the fluvial geomorphology and hydrology of Little Arnot Run in the Allegheny National Forest. It's a second-order stream that flows 15 kilometers through a forested catchment with an area of 9.5 square kilometers. Geologic factors appear to be the dominant influence on the valley morphology, its channel slope, the sediment supply, and the water chemistry of the fluvial network, with the first-order streams shown as pale blue lines and Little Arnot Run shown in red line on this map. The orange dots depict the locations of monitoring sites or planned restoration activities. The perimeter of the watershed is underlain by the Pottsville Formation, shown in brown, a clastic sandstone and conglomerate which forms the drainage divides. The valley hill slopes are underlain by the Shenango Formation, shown in rusty orange, and the quarry sandstone through Riceville Formation, shown in yellow. Both are siltstones with steep re-entrance along the valley sides containing lower tributaries that are transport limited, delivering pulses of clay, silt, and sand to Little Arnot Run during storm events. The middle and lower reaches are underlain by the siliciclastic Catskill Formation, shown in blue, which causes the hill slopes to steepen at the valley floor, which is underlain by the Devonian Venango Formation, shown in green. In terms of energy and fluvial processes, it can be helpful to divide this fluvial system into three zones. Firstly, a zone of erosion in the headwater reaches where channel gradients exceed 2%. Secondly, a zone of transport where gradients are between 1.4 and 2%. And thirdly, a zone of deposition where the gradients are less than 1% near its confluence with Arnot Run. There are no carbonate rocks in the watershed, so pHs are slightly low, averaging 6.1 in the headwaters and gradually increasing to 6.7. Glaciation did not occur in this region, but quaternary periglacial processes have left their fingerprint on the land surface. In the lower left, you can see the north-facing hill slopes are lower in gradient than the south-facing hill slopes, implying that periglacial slope processes were, on average, freeze-limited, and more active with a shaded aspect. Nevation features are more common and better expressed on south-facing slopes. The drainage network is shown in blue lines and superimposed upon the surge-go hydrologic soil groups. Over extended period, freeze-thaw and mass wasting processes cut niches and then terraces and then entire cryoplanation surfaces on the higher topography, and it formed colluvial-filled bedrock hollows on the valley hill slopes. The higher elevations overlying the sandstone bedrocks have high infiltration capacities, as shown in pale yellow, and the colluvial hollows in the valley bottom, developed over shale bedrock, have slow infiltration capacities, shown in pale orange. Medium to very slow infiltration soils, shown in red and maroon, are found in the lower part of the valley where the floodplain is underlain by fine-grained alluvial sediments deposited during overbank flood events. In this region, we find the highest concentration and diversity of wetland plants in bogs and vernal pools scattered throughout the floodplain and along the valley margin. During intense runoff events, the stream becomes turbid with suspended sediments delivered from the first-order tributaries in the colluvial hollows. The implications of all this for restoration is that we'll need to be careful about adjusting the channel slope and the sediment transport regime to avoid siltation of benthic habitat. Flow hydraulic models will help us set boundary conditions for adjusting the channel dimensions and the energy grade lines. A detailed survey of stream and floodplain features was conducted along a 6.8 kilometer length of the channel, shown by the red line in this aerial view looking north across the axis of the valley. The survey included mapping the tallweg of the stream, inventorying large woody debris that spanned the channel, describing bed forms and width-depth ratios, measuring the dimensions of the pool and riffle and run and glide and cascades, and conducting pebble counts, as well as taking observations of the channel bed and bank material, root strength, bank height, and cohesiveness, and any evidence of historic alteration. We've also been measuring flow velocity and depth to estimate discharge and get a handle on the distribution of shear stress within the channel. These data will be coupled with numerical flow models to ensure the large woody debris and sediment structures that are planned to be used to reconnect the stream to its floodplain are both self-sustaining over the long term and do not wash out during flood events. At the reach scale, anthropogenic factors are the dominant influence on the channel and floodplain morphology, which remains in a protracted phase of adjustment to alterations done during the 19th and the early 20th century. Logging berms and steam railroad grades remain on the floodplain, as shown in the left photo, and relic oil pipes and exploration pits are scattered throughout the floodplain and in the channel in several places. At least 12 oil pads with J-pumps remain active in the watershed today. All of these factors are under consideration as part of the restoration strategy. For several kilometers, the stream was dredged, straightened, and converted to a single-thread channel that remains narrow and deep and disconnected from side channels. With higher stream powers, the channel continues to degrade, lowering the water table with it. The table in the upper right summarizes a few of the fluvial geomorphic parameters measured during the channel survey, and the longitudinal profile of the stream's tallweg was surveyed over a 1 kilometer length within the restoration reach is shown on the bottom. Essentially what we are discovering is that the channel morphology is highly influenced by bank cohesiveness, root strength, channel slope, abundance of large woody material, and water and sediment discharge. Channel widths decrease and bank heights increase with increasing bank cohesiveness. Pools ranged in depth from 0.6 to 1.7 meters, with large woody debris being the dominant influence on pool spacing and depth. Average wetted widths increased in a downstream direction, reflecting the influence of discharge and contributing area. And the relationship between the channel morphology and bank cohesiveness and root strength is a little more complex, with some root wads in cohesive banks causing deep scour pools. But occasionally the roots would trap large wood debris on the upstream end, which then would trap sediment and initialize a chain reaction of transverse bar formation and growth, which then would shift the tallweg to the opposite bank. In many places you would see simultaneous erosion and deposition, which appears chaotic to most people, but it's wonderful for aquatic life, with new spawning gravels and channel complexity and cover increasing. It's nature's way of establishing a new fluvial equilibrium, and it's guiding our restoration strategy. Here are two cross-sections across the valley. The view is looking upstream, and the photos on top will help you visualize some of the features we see on the floodplain. The present-day channel remains deep and narrow and located along the valley margin. It's disconnected from its former braid channels and other depressions on the floodplain, as shown in the middle photo. Now there may be one or two unpaired quaternary terraces, but much more geomorphic mapping, soil pits and borings, and geophysical surveys are needed to ascertain the architecture of the floodplain surface and the underlying valley fill. Most features are clearly fluvial landforms, but there are a number of relic oil pits and other disturbance features visible on the floodplain. Higher surfaces near the margins of the valley are believed to represent a complex assemblage of alluvium, colluvium, and debris flow deposits, where tributaries merge with the valley floor, as shown in the far right photograph. The pebble count data show the typical decrease in sediment size in a downstream direction, with pools consisting predominantly of well-sorted sand and gravel, with a D50 of about 20 millimeters, and riffles consisting of cobbled boulders with a D50 ranging from 80 to 120 millimeters. Bankful velocities were estimated to range from 1.1 to 2.1 meters per second, with most bed material likely to be mobile during flood events, as predicted using the Hulstrom curve in the lower right. In forested watersheds throughout the eastern United States, stream widths typically increase in a downstream direction, as contributing area, discharge, and stream power causes channel widening to occur. Geomorphologists refer to this as hydraulic geometry. On the left is a plot showing changes in bankful width on the vertical axis with catchment area on the horizontal axis for watersheds in central Pennsylvania and Maryland, from John Clune's USGS publication this year in 2020. Streams in non-carbonate are shown in black triangles and carbonate settings are shown in blue triangles. I've superimposed upon this Little Arnot Run shown in red dots. What you see is in the upper reaches, where drainage area is less than 2 square miles, average bankful width of the channel compares favorably with other streams in central Pennsylvania. However, as one moves downstream, increases in bankful width, shown by the red trend line, tend to be less than most other catchments in Pennsylvania and Maryland. I believe this is because the channel remains narrower as a result of historic alterations done to it, primarily dredging, straightening, and berming, to accommodate log drives and the construction of a narrow-gauge railroad that ran up the valley. The stream remains in a protracted phase adjustment to these alterations, with channel widths increasing at a much lower rate than we typically find in unlogged watersheds. Particle size, as measured by pebble counts, shown being conducted in the photo, generally decrease downstream, and they increase with slope, because increasing shear stress and transport capacity being highest in the steeper headwater regions of the watershed. Here, the grain size counts are shown plotted on top of the figure of Lucian Brush's classic 1961 USGS professional paper entitled Drainage Basins, Channels, and Flow Characteristics of Selected Streams in Central Pennsylvania. Most of the stream is shaded completely by mature forests, with little to no direct solar radiation. Diurnally, water temperatures vary between 2 and 4 degrees Celsius, showing the greatest variability during the low-flow periods in late summer and fall, when air temperatures vary considerably and buffering from groundwater inputs are low. The seasonal cyclical nature from winter into spring and then the summer and the fall are shown by the week-long moving average in black on this plot. And you see that the average temperatures during the winter are low, around 1 degree Celsius. They increase to a little over 6 degrees Celsius during the spring, March through May, and as much as average 16.1 degrees Celsius during the summer months of June through August, and 7.8 degrees during the fall. Average annual groundwater temperature that's measured in the piezometers is shown in the pale green line, and you can see the importance of stream bed conductance and mixing on stream temperatures. They keep the river warmer than the ambient air temperatures during the fall and winter. Temperatures increase 6 to 8 degrees between May and October, predominantly from long-wave atmospheric radiation during the hot summer months. Shading effects and southern hill slopes are also evidence, with tree canopy moderating the variability during the hot summer months and topographic shading during the winter months, when much of the valley bottom remains in the shade due to the low incident angle of the sun and the high relief of the adjacent hill slopes. Not shown here are the longitudinal variations in stream temperature. During the summer months, temperatures increase on average a little over 0.8 degrees Celsius per kilometer in a downstream direction, largely a result of long-wave atmospheric radiation. Contributions from tributaries following runoff events also influence the temperature in the main channel. Flows in the stream are relatively short-lived in response to rainfall runoff and snowmelt events, with a time of concentration of less than 6 hours and a long recession curve, depending upon the amount and the duration of precipitation or melt. Elevations of the stream and the groundwater surface are recorded every 15 minutes in a network of piezometers and gauge stations we installed in the channel and the adjacent valley alluvium. Hyporheic exchange is the mixing of surface and shallow subsurface waters through porous sediment that surrounds a stream, and it is driven by spatial and temporal variations in the channel characteristics such as stream bed pressure, bed mobility, the alluvial volume, and the hydraulic conductivity of the valley alluvium. So what we see here is that following rainfall runoff events, as stream levels and stream bed pressures rise in the channel, hydrostatically driven exchange occurs as surface water mixes with groundwater in the valley alluvium. During the drier periods in late summer and early fall, evapotranspiration and uptake by forest roots, those losses are so significant that you can see where piezometer P3A ran dry. It was a hand-dug well that extended only 1.6 meters below the valley floor. This figure is a conceptual model of how surface, hyporheic, and groundwater flow domains interact within the Little Arnot alluvial valley. The hyporheic zone is defined by the extent of surface and subsurface mixing, called hyporheic exchange, through the porous sediment surrounding the stream, and it's characterized by circulation cells that move surface water into the surrounding alluvium and back to the river again, and is shown by dashed red arrows on this figure. Hyporheic exchange is distinguished from far field inflow of groundwater, shown by the yellow arrows, and from one-way outflow of river water. In other words, flow paths that do not circulate water from the river and then back again to it. The time series shown in the previous slide suggests that we see the signal of both far field inflow and groundwater from the valley hill slopes, some outflow of water, and significant hyporheic exchange. Despite orders of magnitude changes in discharge, in piezometers that are located near the channel, we find relatively little variation in transport down valley gradient along hyporheic flow paths at distances of up to 100 meters from the channel. Indeed, subsurface transport appears to be largely insensitive to in-stream discharge, and these patterns are explained by this conceptual model in which both the stream and the subsurface flow are in parallel along the valley bottom. The subsurface flow appears to remain nearly constant through the season, given the largely unchanging geologic setting of the valley. In other words, hydraulic conductivity field, the large roughness elements, the fixed bedrock constraints, and the down valley hydraulic gradients. And this is good news for the proposed restoration efforts next year, because as they try to raise the channel bed, we anticipate this will result in significant increases in hyporheic exchange. This is a time-lapse video of the stream showing effects of lateral inflows from the nearby hill slope on the right and hyporheic exchange with the alluvial aquifer on the left. This reach is characterized by a long riffle and is located approximately 100 meters downstream of cross-section 3. The water level in the channel and piezometers only 31 meters from the stream, P3A, and 126 meters from the stream, P3B, are shown in the graph in the lower left-hand corner. Hourly precipitation in inches per hour is shown by the blue bars, and if you watch the water levels in the stream, you'll see a nominal amount of base flow, believed to represent far-field groundwater inflow from underlying bedrock and the adjacent hill slope. Between precipitation events, this lateral inflow is sufficient to provide flow depths of 0.2 of a meter across the channel. But here, the channel is located next to the valley wall you can see on the right, and changing lateral inflows from the hill slope appear to interact with the valley bottom bedrock topography, particularly during low flows. In locations such as this, the steeper relationships with discharge may actually indicate dominance by hill slope inputs or by the underlying bedrock topography. Keep your attention focused on the water levels in the stream, and you'll see them rise in response to two relatively minor precipitation events on December 10th and the 14th. The data thus far suggests that reductions in discharge from the hill slope to the stream through baseflow recession explain decreasing water levels across the valley bottom and overall decreases in catchment discharge. I attribute this to the fact that the highly constrained valley is dominated by geologic control. Lateral inflows may have relatively little impact on valley bottom hyporheic flux rates at any given location. In other words, on the valley bottom, we observe responses that are time invariant, where hyporheic exchange is indeed occurring and is strongly controlled by channel morphology interacting with the hyporheic flow net in ways that did not change with changing stream discharge. But much more work needs to be done to better characterize the hyporheic exchange, and it remains a knowledge gap I am most interested in addressing this coming year. We just installed several more piezometers screened deeper within the valley alluvium, and we hope to conduct some tracer tests and more aquifer tests to discern flow paths, flux rates, measure aquifer properties such as porosity, hydraulic conductivity, and specific yield, and determine the degree of heterogeneity and anisotropy of the valley alluvium. Thank you very much.